So, good morning, friends. How are you? Okay, everyone is fine. So, hope you all have revised all the previous topics, design of a stator, rotor, and all the formulas and the calculations. You must have revised. Now, we will go ahead with the performance calculation, which is most important part of three-phase induction motor. So, the first one is efficiency. Eta equals to output upon output plus loss. What are the losses? Losses are stator copper loss, rotor copper loss, stator iron loss, friction and windage loss, a stray loss, that is 1% of input power. Once again I am repeating, efficiency eta equals to output upon output plus loss, and losses are stator copper loss, rotor copper loss, stator iron loss, friction and windage loss, a stray loss, 1% of input power, that will be. Stator copper loss, length of mean turn empirical relation LMT, length of mean term L plus 2.3 tau plus L plus 0.24. That means L is go conductor, 2.3 tau is overhang, L is return conductor, and 0.24 is connections. So L equals to gross length of the stator. Tau is the pole pitch and all dimension in meter. So you can look over here, this is the go, this is the overhang, and this is the return, this is the finish. Start, go, overhang, return, and then finish. So resistance of the stator winding per phase RSPH equals to 0.021 into LMT into TPH upon AS. So LMT equals to length of mean turn in meter, TPH equals to turn per phase in stator, AS equals to cross section of stator conductor in mm square. So total stator copper loss PCUS equals to 3 into IS square into RSPH. So total stator copper loss PCUS equals to 3 into IS square into RSPH. Now IS equals to stator current per phase. So length of the rotor bar. So length of the rotor bar LB equals to L plus allowance for a skewing. Allowance for a skewing. These are the skewed rotor conductor bars. These are the end rings, and this is the skewed rotor conductor bars. A skewing is done normally for one slot pitch length, stator slot pitch. So a skewing is done normally for one slot pitch length. So LB equals to L root under L square plus tau SG square. So rotor bar resistance RB equals to 0.034 into LB by AB. You please keep noting. Rotor bar resistance RB equals to 0.034 into LB by AB. Total copper loss in the rotor bar PCURB equals to IB square into RB into number of rotor bars. Number of rotor bars equals to number of rotor slots, that is equals to SR. So PCURB equals to IB square into RB into SR. Copper loss in end ring, mean diameter of the end ring DME. Mean diameter of the end ring DME is assumed as 4 to 6 cm less than that of rotor. So DME equals to DR minus 0.04 to 0.06. Mean diameter of the end ring DME is assumed as 4.6 cm less than that of the rotor. DM equals to DR minus 0.04 to 0.06. Mean length of the current path in end ring LME equals to pi DME. So resistance of end ring equals to 0.034 into LME by AE. So total copper loss in end ring PCU, total copper loss in end ring PCUE equals to 2 I square RE. So now these all are the copper loss in end ring, rotor copper loss, and now the next topic is core loss. Core loss in stator teeth, stator core. Need to know flux density, stator teeth, stator core. Core loss in rotor is negligible. This loss is mainly in stator. So core loss in the rotor is negligible. Core loss in stator teeth. Flux density at a stator tooth. So calculate flux density at 1 by third height of the stator tooth from its root. Calculate the flux density at 1 by third height of the stator tooth from its root. Then calculate the area of cross section of a stator tooth at 1 by third height from the root. So width of the tooth at 1 by third height and iron length of the core. So this is the air gap, this is the rotor, h by 3 you can consider here. And now width of the tooth at 1 by third height. So width of the tooth at 1 by third height. So diameter at 1 by third height. So diameter at 1 by third height, d dash equals to d plus hs by 3 plus hs by 3. Slot pitch at 1 by third height. Slot pitch at 1 by third height, tau s dash equals to pi d dash by sg. So tooth width at 1 by third height, that is bt dash equals to tau dash b minus bs. Now area of tooth at 1 by third height, area of tooth at 1 by third height, that means width at 1 by third height and iron length. So at dash equals to bt dash into li. Bt dash, this is the bt, so this is the bt, so bt dash into li. You can easily calculate the area of tooth at 1 by third height. Now area of each tooth at 1 by third height, area of each tooth at 1 by third height, at dash, that will be equals to bt dash into li. So you can keep noting all these formula and just keep all those formula in the boxes, that will help you in during the calculation and calculating all the parameters. So now iron area in tooth, iron area in the tooth at 1 by third height per pole. So ATP dash is equals to AT dash into teeth per pole. AT dash into teeth per pole. So ATP dash equals to AT dash into SS by P. ATP dash equals to AT dash into SG by P. So flux density at 1 by third height in teeth, that is BT dash equals to flux per pole divided by total area per pole at 1 by third height. So BT dash equals to flux per pole, tooth area per pole at 1 by third height. So BT dash equals to phi by ATP. So BT dash equals to phi by ATP. So now calculate the volume of all the teeth in the stator. So VTS equals to ATP into HS into SG. ATP dash into HS into SG VTS. So weight of all teeth in the stator, weight of all teeth in the stator WTS equals to VTS into raw iron. So raw iron, that is 7860 kg per meter cube. This is the so 7860 kg per meter cube. Corresponding to the operating flux density in the stator teeth, iron loss per kg of the material can be found out from the graph. This flux density versus loss what graph. So corresponding to the operating flux density in the stator teeth, iron loss per kg of the material can be found out from the graph. So multiply this specific loss value total weight of the stator teeth. So core loss in the stator teeth. Now calculate the area of cross section of the core. Now calculate the area of cross section of the core. So ACS equals to DCS into Li. ACS equals to DCS into Li. So calculate the mean diameter of the stator core. So DCMS equals to D plus 2HS plus DCS. Now calculate the volume of stator core. VCS equals to ACS into pi D CMS meter cube. So by putting all the values you can get the result. Now calculate the weight of the stator core. WTCS equals to VCS into raw iron. Corresponding to the operating flux density in the stator core BCS, that was chosen earlier, iron loss per kg of the material can be found out from the graph. So multiply this specific loss value with total weight of the stator loss and core loss in the stator. So now the another loss will be friction and windage loss. Friction and windage loss. So you can learn the value for suppose that 0.75 kilowatt motor is there. So friction and windage percentage of output, okay, friction and windage loss, the bracket, you can say that percentage of output will be for 0.75 5.5%, 7.5 kilowatt 2.7%, 150 kilowatt 1.0%. So finally we can conclude that efficiency eta equals to output by output plus losses. Efficiency eta equals to output by output plus losses, and losses will be stator copper loss, rotor copper loss. In rotor copper loss, bar and ring, stator iron loss, friction and windage loss, stray loss 1% of input power. So in this way you can easily calculate the basic design of the 3-phase induction motor. So there is too many things we have to learn more. This is the, you can say that, surface level of the design, and further we can go very deep and we can have more insight of the design. So we will try to continue in the next lecture. That's all, and thank you. Have a nice day.